Yeah, go ahead.
Our next talk is by Mehdi Hossain Sadi, talking about implementing optimization-based control tasks in CPS with limited computing capacity. The floor is yours.
Thank you. So does it show up? Do you see my slides?
We see that well, yes.
Okay, awesome. So my name is Mehdi, and today I'm going to talk about implementing optimization-based control tasks in cyber-physical systems with limited computing capacity. Assume that we have a dynamical system. It's a dynamical system in this form. We have a dynamical system. We use a given sampling time to discretize the system. Here, X is the state of the system, U is the control input, and Y is the output of the system. The control objective is for a given desired reference, which is denoted by R, to control the system such that the output of the system converges to this desired reference asymptotically, and such that the state of the system and the control input belong to two compact and convex sets denoted by curly X and curly U. So having this problem, several solutions, several approaches have been proposed in the literature to solve this problem. Two popular solutions are model predictive control and reference governor. In model predictive control, we need to solve an optimization problem at every time instant, and this optimization problem gives us the control input. But in reference governor, first we ignore the constraints, we stabilize the system. For instance, we can use a state feedback controller to stabilize the system. Then again, we solve an optimization problem at every time instant, but this time reference governor framework gives us the auxiliary reference that should be applied to the system. But regardless of these natural differences, as you can see, we need to solve an optimization problem at every time instant. So what we need just a processor that we need a processor that should solve an optimization problem at every time instant. Here, Z is a general variable. If we talk about the model predictive framework, it will be the control input. If we talk about the reference governor, it will be the auxiliary reference. G0 is a strongly convex objective function, and the constraints on the state and control input can be expressed as NC inequality constraints. GI is a convex function. So as you can see, it's a convex optimization problem. But usually it's not the case in today's cyber-physical systems. In today's cyber-physical systems, there are multiple safety critical control systems that are implemented on a single processor. So here you can see an example. We have 4 control systems implemented on a single processor. So it means that we will have limited, variable, and unpredictable computing capacity. Such scenarios exist in different applications, like self-driving cars, robotic arms in industrial sites, UAVs, UGVs, airplanes, and many other examples we can mention here. Several attempts have been reported in the literature to address the issue of limited computing capacity. Let's start with taking a look at the real-time scheduling literature. Roughly, we can divide the existing methods into 2 groups. The first group is fixed sampling period. So first, we need to determine the worst-case execution time of each control task, and then using an available policy, a given policy. For instance, here I've used earliest deadline first policy. We can determine the sampling period of each control task. But since optimization-based control tasks have a large execution time, the resulting sampling period will be large. So it means that but unfortunately, the larger the sampling period is, the worse will be the control performance. Here you can see an illustrative example carried out on a double integrator. As you can see, as we increase the sampling period, the control performance, which is the tracking error, becomes larger and larger. The second group are called mitigative schemes. So in this case, instead of considering the worst case execution time, we consider a relaxed upper bound, kind of optimistic upper bound on that. And based on this relaxed upper bound, we determine the sampling period. But at runtime, if the execution time exists, this upper bound, we modify the control parameters of all control systems such that they can compensate the increase, the impact of increase. This group of schemes has been shown to yield a better performance and to lead to a reduction in the underutilization of computational resources, but unfortunately there is no systematic method to compute the modifications, and even there is no guarantee that such modifications exist. And also they don't consider the constraints satisfaction, because this increase may lead or may bring the system to a situation that is impossible to guarantee feasibility. This issue has been discussed in the constraint control literature as well. There are multiple, again, solutions, multiple attempts to address this issue. One is offline computation. You can see this idea in the explicit model predictive control. Here we divide the region into multiple polyhedra, and then at runtime we just need to determine the region containing the current state, and then we can use the pre-computed control input. But they require a lot of memory, and also they are not robust to early termination of the search for the region containing the current state. The second group are self or event triggered control. Here we use a triggering mechanism. So we have a triggering signal. If this triggering signal exceeds a threshold value, we compute the control input. But the main issue is that there is no guarantee that when the triggering mechanism invokes the control task, there will be enough computational power to compute the control input. And the last and the most recent attempt are dynamically embedded model predictive control. Here, we can embed the solution of a model predictive control into a virtual dynamical system, and this virtual dynamical system should be run at in parallel with the system. And it has been shown that the solution of this virtual dynamical system converges to the optimal solution. But they cannot, in general, they don't guarantee recursive feasibility, and since they have employed some conservative solutions, conservative tools, the resulting solution is in general conservative. There are other attempts as well, like anytime model predictive control and other schemes, but as far as I know, they don't guarantee recursive feasibility. With that motivation, we argued that we need a robust to early termination optimization to be able to address this issue completely. So we introduce this robust to early termination optimization in this paper. Underlying the idea is combining primal dual gradient flow with the barrier function. So we have an optimization problem in this form. We use this barrier function. As you can see, it's not the standard barrier function. It is kind of modified. We tighten the constraints by 1 over beta, and we will see later why we do that. And then based on this barrier function, we use the primal dual gradient flow, and we end up with this continuous time dynamical system. Here, Z and lambda, Z is the primal parameter, lambda is the dual parameter, and Z and lambda together are the states of this virtual dynamical system. Sigma is the design parameter, and phi is the projection operator, just to make sure that the derived parameter remains positive at all times. This continuous time dynamical system has two main properties. The first one is that the states of this dynamical system converge to the optimal solution or the optimal values exponentially fast. And the second property is that the states remains feasible at all times. I'd like to start with the first property. In order to prove the convergence property, we use Lyapunov theory. Lyapunov theory is a very powerful tool to study stability or convergence of dynamical systems. It's based on a positive function, which is called Lyapunov function, which can be seen as a generalized energy function. If the time derivative of this function is strictly negative, it means that the energy of the system is decreasing over time, so it will converge to the equilibrium point. We use this tool, and we introduce this Lyapunov function, and then just by doing some math, we showed that the time derivative of the Lyapunov function satisfies the first inequality, and we can also conclude that it satisfies the second inequality. The second inequality means that the difference between the states of that virtual system and the optimal values decreases over time exponentially fast. Regarding the second property, that the states remain feasible at all times, we use Alexandrov's theorem. We know that the feasible set of the optimization problem builds a polyhedron, or it can be inner approximated by a polyhedron. So we use Alexandrov's theorem, and we show that if we start from a feasible initial condition, a point inside these polyhedron. We will never exceed these polyhedron. As we approach the boundary, there will be a repulsion term pushing back the trajectory toward the inside of these polyhedron. These two properties together give us allow us to start solving an optimization problem without worrying or with no concern about the early or premature termination. We can start solving the optimization problem whenever it's terminated due to limited computing capacity. The solution is suboptimal due to the first property, and more importantly, is feasible. So in model predictive control framework, in reference governor framework, that we need to solve an optimization problem continually at every time instant, when we can guarantee feasibility at every time, it means that we can guarantee the recursive feasibility as well. So it's an optimization approach. It means that we can employ it in different control frameworks. First, we applied it to reference governor framework, and we studied vehicle rollover prevention. And here you can see our numerical results. We considered fishhook test, which is a standard test to study rollover prevention. It's a severe steering, counter-steering maneuver. You can see we have also compared our scheme with reference governor with small and large sampling period. As you can see, this optimization approach can guarantee constraint satisfaction with a small degradation in the control performance. We also considered this scheme in a model predictive framework, and we studied its effectiveness on F-16 aircraft. We considered, we assumed that there is a processor which should take care of longitudinal and lateral control. And here you can see the results that we can guarantee constraint satisfaction at all time with a small degradation in the control performance. So in this presentation, we have seen limited computing capacity is an issue in cyber-physical systems, and prior work does not address this issue completely to the best of our knowledge. And with that motivation, we argued that robust early termination optimization is a promising approach to address the issue. We developed a primal dual gradient flow combined with a barrier function method to address this issue. The developed scheme, we showed that it converges exponentially fast to the optimal solution, and it guarantees feasibility at every iteration. And since it's an optimization approach, we can use it, we can employ it in different control frameworks. We did it on model predictive control and reference governor, and we also showed some simulation results as well. Future direction will we will investigate the impact of discrete time implementation, because to prove the properties we use continuous time, the properties of continuous time world. But our numerical results show that if we implement this in discrete time with a sufficiently small sampling period, the properties are maintained, but we need a strong certificate for that. The second direction will investigate how we can extend this idea to a time-varying optimization problem. And finally, we will consider how we can develop a distributed, robust early termination optimization approach. So at the end, I should thank my co-authors, my collaborators, Bruno Sinopoli and Sanjay Barua from Washington University in St. Louis, and also Ilya Kolmanovsky from University of Michigan. And I should also thank National Science Foundation because they financially supported our research. Thank you very much for your time, for your attention. I think we have time to take some questions, but if you have further questions, this is my email address. Please feel free to send me an email. I'd like to keep a discussion going.